we were talking about valence bond theory of H2 molecule, and in the previous module I talked about uh, setting up of hydrogen atom, Hamiltonian, setting up of hydrogen H2 plus molecule ion Hamiltonian, and setting up of H2 molecule Hamiltonian. And then I simplified this Hamiltonian with the help of Born-Oppenheimer's approximation, and you saw the Hamiltonian in the atomic unit also. And thereafter I started solving the equation H psi is equal to E psi. Okay, and we have written the Hitler-London wave functions, and for that function we started solving the H psi is equal to E psi. Okay, and finally what we got from the secular determinant was the two energy levels, E plus and E minus. So this I did in the previous semester, and then I said you that the S function, which is the overlap integral, this integral can be solved using an elliptical coordinate, and the value is in terms of R. R is the internuclear separation. So in terms of R, you can get the value of S, and if you look at this one, there is an exponential decrease in this form, and all the parts within the bracket are positive terms. You have a solution of this. If you want, you can get in a book, Macquarie's book, or some other books also. You can get the solution, but it's not needed, so I have not done it. But S orbital functions. So what you are getting is, we are solving the different integrals which is present in the energy equations. In energy equations, you have H11, H12, and S square. So S value solution I have given you, and now I will see that how to find out the H11 values. H11 values is again an integral where you have those value is psi 1 H psi 1 d tau. So H11 is psi 1 H psi 1 d tau, and the psi 1 is again Hitler-London wave function. I said you it's psi A1, psi B2 function, and the other one psi 2 will be psi A2, psi B1 functions. So electron exchange will take place with the nucleus in the writing the psi 2 value. So for H11 you have psi 1 H psi 1 d tau, and for H22 you will have psi 2 H psi 2 d tau, and both will give the similar value, and there is no point in saying that one will be different from this one because both are hydrogen atom. So you will get the same integral value for H11 also and H22 value also. In the previous module I have written the Hamiltonian, and now in this form I have not written. Now it is written in the form of atomic units. Okay, because it was E square there, and now in atomic units the charge present on the electron and is 1 charge, so is on the proton, so all E square becomes equal to 1. So this is an equation, this is an Hamiltonian in atomic units. Okay, now for H11 what you can write is this is your psi 1, this is your psi 1, psi A1, psi B2, and then you write the Hamiltonian. All this is Hamiltonian. All this is Hamiltonian, having 1, 2, 3, 4, 5, and 6 terms, and then again psi 1 d tau. Okay, so I did nothing but just I have written this H11 integral in the form of writing the actual Hamiltonian and writing the actual wave function psi 1. Okay, we have to solve this integral. So how can we solve this one? Let's first do this. I have regrouped this one. These two terms of the Hamiltonian, minus 1 by 2 del E1 square minus 1 over R1, and plus again within bracket 1 by 2 del E2 square minus 1 by R2. So these two, if you look at the closely, then this is nothing but a Hamiltonian for hydrogen atom. Okay, so this is a Hamiltonian for a hydrogen atom. If you remember, hydrogen atom, you have electron and proton. So what do you write? You write minus h cross s square divided by 2m. Del square means del square, and then you have, for the potential energy, you write minus E square by R. And in terms of if you write in terms of atomic unit, then this is what you write: 1 minus 1 by 2 del square minus 1 by R. So this is what is 1 minus 1 by 2 del square minus 1 by R. So this is a Hamiltonian for hydrogen atom. For hydrogen atom, there should not be any confusion why I have clubbed these two terms. So same is the case with this one also. And now if you want to solve separately this Hamiltonian with the wave functions, then this what you are doing, this is your operator and this is your function. So you operate with this operator, with the whole operator H on the psi a1 psi b2 function. So I will do it separately for the first operator, minus half del square minus 1 by r1 on psi a1 psi b2. If you operate this, what do you get? Your equation should be like this one. Now this is an r1, okay. So there will be no effect on psi b2 because psi b2 will remain constant. So psi b2 comes out, and when you operate with a Hamiltonian on psi a1 function, what do you get? You get the EH value, energy of hydrogen atom, and the psi value. So what you get is energy of 1s atomic orbital and psi a value, because you know for a hydrogen atom you can write H psi is equal to E psi. Okay. So this is your H, this psi a1 you are operating, psi b2 becomes constant. So psi b2 is here, and then you have E1 as psi a1. So now hydrogen atom energy E1 is in atomic unit is minus 1 by 2. So what you can write is this equation you can write as minus 1 by 2 psi a1 psi b2. If you operate with the Hamiltonian of other hydrogen atom, that is 1 by 2 del square E2 square minus 1 by R2, that also similarly is operated, and you have now it will operate on psi b2. So psi a1 will become constant in the next case. So psi a1 becomes constant, and then also you have 2s energy. Sorry, this is not 1s energy, it is 2s, it's also 1s energy. So when you say it is for the second atom, okay, 1s energy, and then psi b2 you get, okay. But this is for B hydrogen atom and this is for A hydrogen atom. That differentiation you can make, okay, because in hydrogen you do not have 2s orbital, so don't get confused with 2s. I have written 1s A and 1s B. So this is for the B hydrogen atom. So psi b2. Now and naturally both the hydrogen will have the same energy, minus 1 by 2 atomic unit. So if you write minus 1 by 2 atomic unit, the equation comes out to be this one. So what you can do in the previous equation, this lengthy equation on this last equation on this slide can now be a little simpler by writing this one. So psi a1 psi b2 remains, then this so I do have the same equation. We have solved this one, operation by this Hamiltonian and operation by this Hamiltonian is already solved. Minus 1 by and everywhere you get at both the places what you get, minus 1 by 2 psi a1 psi b2 minus 1 by 2 psi a1 psi b2. So both have the same value. So this you can sum it up and you can write minus 1, and then again psi a psi b2 is psi a1 psi b2 is there. So that psi a1 psi b2 comes here, psi a1 psi b2, and rest 4 terms of the Hamiltonian 1 by Ra, 1 by Rb, 1 by R12 and 1 by R capital R remains in the Hamiltonian, because two part of the Hamiltonian we have solved, and we have written in place of that minus 1. Or what you can write in place of that, you can write the energy of 2 hydrogen atom, 2 EH also you can write, okay. That's the same thing. But rest of the term remains minus 1 by Ra, minus 1 by Rb, plus 1 by R12, plus 1 by R psi a1 psi b2. Now what you will do, you will operate with this function on these part of the Hamiltonian separately, or you will segregate them with the different integral. So how to do that? So this integral we can segregate, and I have written the function here, first function as such, and then minus 1 by Ra, only one part I have taken, and again the second wave function is psi a1 psi b2 d tau. Now you see here you have psi a, hydrogen atom A also, hydrogen atom B also, and electron 1 also, electron 2 also. So it will be a double integral, and there is a mistake. I'd add this one del tau 1 and tau 2, both should be there because we are integrating in two different space. So it's a double integral, and now it's a complete. So everywhere I think d tau is written. So write d tau as d tau 1, d tau 2. Okay. So psi a1 psi b2 minus 1 by Ra, psi a1 psi b2 d tau 1 d tau 2. So the first part of the Hamiltonian I have taken here. Then similarly you can take the second part. So plus again double integral psi a1 psi b2 minus 1 by rb psi a1 psi b2 d tau. Then r12 you have, so it's a plus r1 by r12 and the same function, a double integral is there. Then you have 1 by r, which is internuclear separation. So again 1 by r psi a1 psi b2. So we have divided this equation into different integrals. Okay. What are these integrals tells you? And now you see, if you have you are taking minus 1 by ra, then psi b will become constant. Psi b will not operate. Okay. So psi b d tau will be equal to 1. So this will go outside again. And now it will be psi a1 minus 1 by ra psi a1 d tau. This term also will be psi b2 minus 1 by rb psi b2 d tau. And now r12 will have both the functions psi a1 psi b2 psi a1 psi b2. So r12, and for this 1 by r internuclear separation also both functions will be there, psi a1 psi b2 psi a1 psi b2. Okay. If you look at this in the first integral here, this tells you about the electrostatic attraction, okay, between the electron 1 and the nucleus. Okay. Again if you operate with this one, this also is the same thing, electrostatic attraction. Psi a1 psi b2 is an internuclear repulsion term, and 1 by r is also an it's an inter-electronic repulsion term, third term, and the fourth term is inter-electronic repulsion. So these are Coulomb integrals. Okay, they talk about electrostatics, and these are Coulomb integrals. So the first two integrals is actually two-centered, one electron attractive energy. Okay, two-centered means you have one nucleus and one electron, two-centered, and it's attractive energy between nucleus and the electron, and this is represented as J, minus J. It's minus J. Okay, so it's minus J. First integral and second integral. The third integral is actually two electron repulsion, two-centered, two electron repulsion. Okay, again you have one electron and second electron, so two-centered, and there is a repulsion between the two. So third electron is repulsion between the two terms. Okay. So this is given as plus 1 by r12, and this is given a plus J prime C. Now somehow this fourth integral I have written as only 1 by r. Okay, it will depend on only the internuclear repulsion. This is also a repulsive term because internuclear repulsion we are talking about. Okay, so all these four integrals are actually Coulomb forces, sometime attractive, sometime repulsive. So these are called Coulomb integrals. These are part of the Coulomb integral. J is a Coulomb integral. Now if you so what will be the total energy? EH part we have already done, that is not here. Hydrogen atom solution. So the total energy H11 will be equal to 2 multiplied by energy of the hydrogen atom, that this part we did in earlier, and then you have J prime minus 2J. So it is J prime. So the total Coulombic energy is J prime minus 2J. So this is somewhere, this is minus J, this is minus J, this is plus J, this is not prime. You remove prime from here. Okay. So then you have J minus 2J. This is not prime. This is plus J only, not prime. You remove the prime. Okay. So you have, and add the prime here. Okay. So that's a mistake on the slide. You correct it. So now you have the energy equal to J prime minus 2J. So you can write J prime minus 2J plus 1 by R. This J prime minus 2J is normally shown as a capital J. This is a Coulomb integral. And again, this J is what? It's a summation of three different terms. One is this one, first integral, second integral, and third integral. So this J again talks about attractive interaction, Coulombic attraction, or its attraction. This is also attractive interaction. This is repulsive interaction. Okay. So you need to solve this J value, and again J value can be solved using elliptical coordinates. And what do you get the J value? J value you get as exponential minus 2r. Again the value is decreasing. 1 by r plus 5 by 8 minus 3 by 4r minus r square 6. What does it mean? See, the two terms are negative here, and for a very large value of r, this will, unless you go asymptotically, it will become 0, but for a large value of r, the term is negative. And as the value of r decreases, the function dips, okay, and it has a minima. It's a negative term in r, so it shows a minima. And then again, for smaller values of r, there is a sharp rise in the j value. So if you look with increasing r, the j value decreases, reaches a minima, and again becomes negative. So this value, for some values of r, the function is negative, and we get a minima, which indicates this type of curve you have already seen for the potential energy of diatomic molecules. So this similar curve is obtained for the j value also. Okay. Of course, the quantitatively the dip is a little larger here. It should be smaller than this one. I will talk about this later on. Okay. Now, so S integral we solved. Overlap integral in the previous class I have given you the value. Now H11 value is actually this one in terms of R, internuclear separation. So there is nothing which is you don't know, and you can have a plot of this in terms of R in a J value with respect to R, and you get a plot like a similar potential energy curve which you have come across earlier also. Okay. If H11 is this, H2, there is no point in saying that H22 will be something different, because both are hydrogen atoms and both will have the same wave functions. So H22 also has the same value, 2EH plus J plus 1 by R. Okay. Now, having practiced this one, H12 you can calculate. So that you have psi 1 H, psi 2 d tau, and so you will write here for psi 1, psi A1, psi B2, and for psi 2 you will write psi A2, psi B1. And again on the same way, what you can do, you can write about psi A1. The first function which you can write is, if I write psi A1, psi B2, then within this del E1 square minus 1 by R1, and again you write this one psi A2, psi B1, psi A2, psi B1. Okay, d2. So it's R1. So your function will be actually psi A1, then H, I am writing in short form, H Hamiltonian for hydrogen atom, then you write psi A2 d2. Okay. Psi A2 d2. So this is hydrogen atom. This is also hydrogen atom. Okay. Of course, the electron is changed, but the identity doesn't change. But here you will have psi A1, psi B2 and psi B1. This integral will not be equal to 0. Okay, this will be equal to S. So if you solve this equation, this integral in details, you will find that what you get is S square with the EH value. Okay, so you practice it. I have just given you an example, which I am going to remove. Okay, because this knowingly I have not done H12 equation. You find the H12 value. So the integral is this one, and this you have to solve. Okay. Now, if you have H12, then the value comes out to be in terms of K, and K again is called net exchange energy. Okay. We do not have any classical counterpart for this, and it is purely an outcome of quantum mechanics. So exchange energy means electron is being exchanged from one place to another place. Okay, and this gives rise to the later on the concept of resonance also we will be talking about. Okay, so you get the similar equation for H12, except you have J in place of J, you have K here, which is again an integral which one can solve, and I will give you the value, and with the overlap integral SS square. If you put these values in the expression for energy E plus and E minus, which we have found, then what you write? You write 2EH plus J plus K 1 plus S square plus 1 by R, and E minus is 2EH plus J minus K 1 minus S square plus 1 by R. Okay, and if you find the difference between the two, the difference delta E comes out to be this one. Okay, and so you see the I said you in the plot of J, the dip is a little larger, J dip is smaller, and K dip is much higher. K is much deeper in the sense. Okay, if you plot the delta E value, what you get a minima for delta E plus, and you do not get any minima for delta E minus. So this delta E minus means E minus does not refers to binding, E plus refers to binding only. Okay, so E plus refers to binding, and E minus does not refers to binding, binding state of the H2 molecule. We are talking about H2 molecule. See, delta E plus is negative, and it is less than the energy of the hydrogen atom. Okay, and delta E minus is positive, and it is more than the energy of the EH2. Here EH2 is greater than the 2EH. So this will not, E minus will not refers to binding. Now the minima in the delta E plus curve occurs at 87 picometer. Now quantitatively speaking, if the delta E curve you plot, then the minima in this curve comes at 87 picometer, and bond dissociation energy is 305 kilojoule per mole. The experimentally observed value are 74.1 and 458.32 kilojoule per mole. So now see what happens. What actually the valence bond theory of hydrogen atom should have explained this experimental observation, that the equilibrium at which the two hydrogen atom remains, the bond distance is 74.1 and the bond dissociation energy is 458.32 kilojoule per mole. But this actually you don't get. What you get is 305 kilojoule and 87 picometers. Okay, but you know that what has been experimentally observed is always right. Rest of the thing, what we are doing, we are suggesting a theory, or Hitler and Nundal were finding a theory in order to explain this experimental observation. I said you always that experimental observations are always correct, and by theory you try to explain those observations. So the theory which we have predicted is still far from the actual observations. Okay. Now, the next task is bringing this value closer to the actual experimental value, and for that we will see how to do. And if I talk about the wave functions from which we started, it was Hitler-London wave functions, where I have written psi is equal to C1 psi1 plus C2 psi2. Now the question is that how much of this psi1 psi a1 psi b2 and how much of this psi a2 psi b1 will contribute to the Hitler-London wave functions. Means what is the value of C1 and C2. Okay, and very obviously, without going into the mathematics, one can say that if you are talking about H2 molecules and both hydrogen atoms are same, then C1 must be equal to C2. Okay, and if that is so, then if you take the C1 value as 1, then C2 value will be and contribution will be how much? It will be plus minus 1. So you can write psi plus as C plus psi1 plus psi2 and psi minus as psi minus psi1 minus psi2. Or you can write in terms of original function psi a1 psi b2 plus psi a2 psi b1, psi a1 psi b2 minus psi a2 psi b1. What is the value of this value C minus and C plus? And this you can say is also the normalization constant. So now this normalization constant I think we have done earlier also, and I have given you the value directly. C plus is 1 over root under 2 1 plus s square, and C minus is 1 over root under 2 1 minus s square. If you put these values, then your two functions, one for the bonding which corresponds to the energy of 305 kilojoule is this one, upper one, psi plus, and one which does not have a minima is psi minus. is the lower one. Okay, so the two functions, H11 wave functions, normalized functions, could be written like this one: 1 over root under 2, 1 plus h square psi a1 psi b2 plus psi a2 psi b1, and another is 1 over root 2, 1 minus h square psi a1 psi b2 minus psi a2 psi b1. So both these functions, eigenfunctions, we got. Okay. Now we have, once you have written the wave functions, what you see is that if you exchange the wave functions, the sign of the function will not change in case of the upper one. So we say it's a symmetric combination of wave functions. But if you change the functions in the lower one, psi minus, then it will change the sign of the function, and this is called antisymmetric wave functions. So once we have the asymmetry, all this wave functions, it comes from where? It comes from 1s orbital wave functions. Okay, so this is orbital contribution to the wave functions of the H2 molecule. Now, besides this orbital contribution of H2 molecules, we also know, we have come across with the another property of electron, and which is a quantum mechanical behavior, is the spin function. So electrons do have a spin functions, and I have said you that for electrons, if the spatial part, if the orbital angular momentum is symmetric, then a spin wave function is always antisymmetric. Okay. So the total wave functions of the H2 molecule, if you have to write, then you will combine both orbital part and the spin part. Now, if you suppose that a spin, the two combining electrons have a spin like alpha and beta, then both electron could have an alpha spin, both electron could have beta spin, or one electron could have alpha and another could have beta. So what are the different combinations which is possible for the spin functions? If you look at this one, this picture again tells you that the experimental value is still lower, you have to work out, and then you have the spin functions are alpha 1, alpha 2 means both the 1 and 2 electrons have alpha spin, beta 1, beta 2 means both 1 and 2 electrons have beta spin, and then if you change one electron is alpha and another electron is beta, then you can take a linear combination of the two. And if you take a linear combination, then you can write alpha 1, beta 2, alpha 2, beta 1, and in between you have a plus minus sign. Again, here also, if you have a plus sign, then it becomes symmetric function, because if the exchange will not lead to change in the total function. But if you have a minus sign, it becomes antisymmetric functions. So these are the four different possibilities for the two spins of the H2 molecule molecules electron which is present. Now a combination, how will you combine this? If the orbital moment wave function you are taking symmetric, then a spin function you will take antisymmetric, and if you are taking orbital as antisymmetric, then you will take a spin as symmetric. And if you combine these two, then what you observe is that you have symmetric functions of orbital, and you have only one antisymmetric combination, of the spin function. So what you get is a function like this one. N is the normalization constant. Instead of writing the whole normalization constant, I have written n. Then psi a1 psi b2 plus psi a2 psi b1, and this part is the spin part. This is a spin function, and this is your orbital function. This is your symmetric function. This is your antisymmetric function. Okay. This I talked about while talking about those angular momentum and so on. Okay. So this symmetric combines with antisymmetric, and what you get is, for H2 molecule, you get only one state possible, that's called singlet ground state. Okay. But if you have the antisymmetric wave functions, orbital functions, and then you can combine it with the three different spin functions, all this part, and this part are symmetric combination of spin functions. So a symmetric combination of spin function will combine with antisymmetric combination of antisymmetric wave functions of orbital functions. So you get three different combinations here, and we say that it's a triplet state, and that we say is an excited state. Though in valence bond theory, I said you, it doesn't deals with all excited state molecules so easily, but it's a triplet excited state here. Okay, so we have one ground state and 3 excited state of the H2 molecule. But still we have not achieved the energy and the uh, bond distance which is required, which is as per the experiments. Okay. So what you need to do is that there you can make some corrections to the orbital functions again, and you can add something which is called the ionic structures. So this is your triplet state and singlet state. The energy will be lower for the singlet state because this only gives you the binding energy. This I talked about earlier also. So it's the same energy. Now, so what we include is ionic forms of the and resonance of H2 molecule. What we assume is that there could be a structure of hydrogen atom where till now what we have said, one nucleus is attached with one electron and another nucleus is attached with another electron. But the identity of electron is lost. First electron could be with the second nucleus and second electron could be with the first nucleus, or both way, first with first, second with first, second, all is possible. Okay, that's what we did till now. Now we say that no, it's not just that. What we can say is that both the electrons of the hydrogen could be attached to the same nucleus, and if that happens, you get a negative charge, hydrogen, and the other one becomes positively charged. So you can have ionic structures in the molecule also. So that we write as Ha plus and Hb minus, or the other way around, Ha minus and Hb plus. And we say that hydrogen atom is actually a uniformly covalent bond HaHb, or ionic structure Ha plus Hb minus or Ha minus Hb plus. Okay. How do we represent these functions? So these functions, you see, psi A1, nucleus A has the first electron, and again nucleus A has the first electron. So this tells you that your Ha is negatively charged. Okay. Now here I have said Hb1 and Hb1. So this tells you that Hb1 is negatively charged. So obviously in this case Hb will become positively charged, and obviously in this case Ha will become positively charged. So you have two different structures, ionic structures for the hydrogen atom, and the wave functions could be written like this one. Again, if you have this function, then a linear combination of this you will have to take, or which is contributing to what extent, the first one or the second one, that we have to see. So the total function when we write the first the orbital part, psi A1, psi B2, Hitler-London wave functions, which I have written earlier also. Psi, or valence bond wave functions, you can say psi A1, psi B2 plus psi A2, psi B1. Then you say lambda is the contribution by psi A1, psi A1, and lambda 2 is the contribution of, sorry, it's this is not there, of, you omit this one, psi B1, psi B1. Okay. So this lambda or this lambda prime, whatever you want, gives you the relative contribution of each of these structures, Ha minus Hb plus or Hb minus Ha plus. Okay. So these two together, what we can write is psi for the H2 molecule is psi covalent plus lambda psi ionic. Now again a reminder that the experimentally observed values are 74.1 picometer and this kilojoule. So we will see does this makes any difference or not. Okay. So the total wave function, so we can talk about the relative ionic contribution to covalently combined molecule in the valence bond theory, and this lambda is called the value which tells you that how much of ionic structures contribute to the actual molecule. Okay. If you look at the contribution from different sources, then if you just combine the two hydrogen atom wave functions without doing anything, then psi A, psi B wave functions, you can write the total wave function, and you don't make any correction. Then also just simply combining also gives you a dip in the energy curve, and that's very small curve, small dip, that's 24 kilojoules. So if you have an energy curve, if you want to plot an energy curve and you have a zero here, then there will be a dip like this one in the curve for the uncorrected functions. Then if you talk about Hitler-London wave functions, then the energy which you get is 303 kilo. It's a little deeper, 303. The minima is at 303. Okay, and you see, wait just a second. It's a very poor drawing, but anyway, I would say this is your R. Okay. Now, in the next thing, what I have written is the addition of. I didn't talk much about the shielding, but if we do that, we have not done it. If we do that, then also there is an improvement, and we get an energy equal to 365. And you see the bond distance, it becomes 74.3. It's very close to the actual value, 74.1. So shielding leads to improvement, and again you reach a value of energy wise, it's also improvement, and bond distance wise, it's a very remarkable improvement in case of this one. Okay. So if you plot this one 365, then also you have a dip, and sorry. You see, internuclear separation is gradually decreasing. Okay, so you get this one. So this is your, but this again is 388, and now it's 365, and the final value is 458. So further improvement is addition of ionic contribution, and the value of energy reaches to 388 kilojoule per mole. But the departure from the actual bond distance, that is 74.9. So addition of shielding leads to very closer bond distance. It's very close to 74.1. But addition of ionic structure leads to a little larger bond distance, but energy improvement takes place. It becomes 388 kilojoule. Okay. So addition of bond, if you write the ionic structure, then it is, sorry, like this one. Okay. So this energy minima is less, this energy minima is more. Okay, 74.9. Actually, not that far. It should be very close. Okay, but because this is the minimum. This is the minimum which you get. Okay, so this way, what we do is that we have an observation that the energy of the hydrogen bond dissociation energy of the hydrogen atom is this one, and we have an observation that what is the bond length of the hydrogen atom, and this we are trying to explain. Hitler and London tried to explain through the theory of quantum mechanics, and he did not do anything. He just combined these atomic orbital wave functions in different ways, and he introduced the concept of exchange of electrons, losing the identity of electrons, making E1 and E2 both to move around both the nucleus, and then he said that at the contribution of ionic structures also, resonance structure also, then he said what you can do is shielding effect also you can calculate, and finally what the energy which you get is very close to not exactly the binding energy of the what you get experimentally, but it is a very close value, and this is what is called keeping the identity of the hydrogen atom. He devised a mechanism to account for the observed value of bond order and observed value of bond dissociation energy, and he was successful. He right from 24 kilojoule he went up to 388 kilojoule. So it's very close to the actual value of the experimental observation. And later on, after this the molecular orbital theory came, which is a more general theory, and we will talk about we have talked about, and we will be talking about the molecular orbital theory also. But this is for the H2 molecule, a diatomic molecule. What about other diatomic molecule? Both the hydrogen atoms are same. It could be a heterodiatomic molecule. It could be the atoms could have more than one nuclei, more than one electrons, so that there is more shielding. So we can proceed through for the higher diatomic molecules and heterodiatomic molecules in the same fashion for the diatomic molecules. In the next module, we will be talking about the concept of polyatomic molecules. You can have we can have 3 atoms, 4 atoms, 5 atoms. They have a definite shape also. So, what makes them of a definite shape is called hybridization. And in the next module, I will be talking about hybridization. Thank you.